Let's now discuss how we humans have represented information about our world using digital structures, digital automata, and other forms of knowledge representation. This has allowed for us to really take the symbolic approach to developing AI. And though we've moved away from some of our roots in symbolism, we still take these approaches in the ways in which we build modern AI systems today. So, the aim of logic is really the elaboration of a coherent system that allows us to investigate, classify, and evaluate good and bad forms of reasoning. An example of early systems of logic include Aristotelian logic, right? This is demonstrated using the square of opposition that you see in the image below. This particular logical construct allowed us to create all sorts of sequences of statements so that we were actually able to evaluate a particular line of reasoning. So consider, for instance, the hopefully familiar format of a syllogism, also from Aristotelian logic, in which we use a progression of logical arguments to rationalize a particular conclusion. In this case, it's a sequence of premises to help us ascertain the mortality of Socrates. From there, logics like the propositional logic shown here evolved. So we began to integrate logic and philosophy with mathematical constructs, and we used basic symbols to represent concepts and the relationships among them. In the mid 1800s, we then had George Boole, and he gave us what we now refer to as Boolean algebra and Boolean logic. This was a binary system in which we represented variables with truth values of true and false, and this really just allowed us to codify prior logics using more succinct mathematical structures. So in this image, we see a truth table demonstrating the basic logic of our syllogism regarding the mortality of humans. By this point in time, we'd already developed the capacity to represent logic using algorithms, where an algorithm is simply the logical sequence of statements to allow for formal reasoning. The word algorithm actually comes from the Persian polymath Al-Khwarizmi's name. He was the first one to actually describe this approach. So the marriage of Boolean logic combined with an algorithmic approach really set the scene for what came next. Digital logic. So scientists like Claude Shannon were really interested in using logic to create code in digital systems. This breakthrough was really possible when Claude Shannon invented the logic gates, right? There were these switching circuits that we were able to use, in which we were able to use combinations of transistors and other electronic components like switches to be able to then create logic functions, like the AND function that you see in the image here, right? So you could take two inputs like true and false and spit out a logical statement. In this case, true and false makes false, as shown in the truth tables on the left. So now we're really cooking with fire. So in his 1950 paper, he described all sorts of logical constructs that he hypothesized were now possible. I find it funny that he sort of talks about these as perhaps of no practical importance, which if you look at the list that he has here, which are things like machines for designing filters and equalizers, machines for making strategic decisions, machines capable of orchestrating a melody, these are things that we are actually using machines for, right? This is literally a roadmap for design for the things that we did with machine intelligence in the years to follow. So as humans started to try to think about how to write, speak, and code, we had to start to grapple with some of the fundamental challenges when creating programming logic. So when we write code, for instance, or even speak a sentence, quite frankly, we're imbuing our sentences with meaning, right? So we're using these particular structures to allow for understandability. So syntax is the term we use to describe the structure of a sentence or even the structure and grammar of a line of code. In this example, the closing quotation mark in my sentence is missing. And so the computer would not actually be able to parse this, and it would report, oop, a syntax error happened, and it would cause me to go hunting for that crazy little syntax error. Semantics, however, are much trickier, right? It's this idea of what a sentence or a line of code actually means. In my example, I could fix the syntax like shown below, and the computer would parse it, but it still doesn't make, in this particular case, Socrates literally immortal, right? So this is an example of how a line of code can be syntactically correct, but semantically problematic. Noam Chomsky offered us this funny example in his 1957 paper on linguistic modeling, where he gave us a sentence, colorless green ideas sleep furiously. It is a perfectly well-constructed sentence, and it means gibberish. I took that sentence and I put it actually as a prompt into the generative AI art tool Lexica to see what type of meaning it would create out of the image. And you see a variety of black and white green women sleeping as this AI tool's best approximation of what the sentence means. So meaning is a very hard thing for us to really convey, even when we're using perfectly correct language. What this really demonstrates are these limits to understanding that we need to overcome. If our goal is to create AI, not just a parrot that mimics my mathematical logic, then I need productive tests also to evaluate whether or not the tool I've created is intelligent or actually understands, right? In addition to good definitions of what I define as intelligence. So in the Turing test proposed by Alan Turing in the 1950s, a human interrogator will actually ask a series of questions to the machine. If the person can't tell the difference between human and computer, the machine essentially passes the test. But this relies on evaluating a set of heuristics that then govern your basic machine logic system, or a primal artificial intelligence, on whether or not it is actually able to perform like a human, right? We're going back to this idea over and over again. So in this case, we're again testing a machine on whether or not it is human-like. But it's not even clear that machines have understanding even when they have the words, right? If I play with that syllogism that we talked about earlier, you can see that I would create something that reads like perfect rational language, but we know that it's gibberish. You know that jigglebugs and broggleblotz are my gibberish words in a rational form, though the machine may not be able to distinguish sense from reference without additional context or data. In 1982, the German philosopher Frege wrote a paper that roughly translates to on sense and reference, in which he differentiated between the name of a thing and a thing itself. So this is the concept and the object. So when I say warbler, that's the name of a bird. And if you know your birds, then when I say warbler, that word is both a reference to a real thing, you understand what I'm saying, and we are able to communicate and understand each other. So the challenge again remains, how can or should we determine how machines think and act? And really, when you think about the basic task ahead of us, it's not so basic, right? How can we provide logical instructions in the form of algorithms, first to perform some of those basic tasks, and then eventually to perform more complex forms of reasoning? To reconcile the challenge of representing knowledge, we have approached the design of automata as abstract machines. So we can now think about these machines as things with some basic rules to determine whether or not something is correct. This concept, this ability to figure out whether something is correct, is known as inference or reasoning. And it's hard, right? Even for us humans. And so we provide a constrained decision space, right? We use this concept of state spaces that describe all possible solutions of a given problem area. So consider this finite state machine, right? So it's the next evolution in state spaces. So consider this finite state machine that's described here. In this turnstile example, there are only two states that the machine can think about. It's either locked or unlocked. And everything in this problem area involves a manipulation of these specific states. If I put the same example in the context of a video game, I could actually create a map in which I map out all of the different possible locations on a physical map that a game character could be in. They could either be stenches or pits or monsters or prizes. I could represent that same information using a representation that a computer would understand, right? So I could take that map, turn it into a grid, assign different parameters to each of these spots, and then create a state machine that actually allows the computer to determine where and what a particular agent is doing in this map. So around 1936, Alan Turing also described a conceptual machine that would eventually be named after him, right? The Turing machine. You may have heard of it. It was essentially a mathematical model that reduces the logical structure of any computing device to its essentials. So with infinite tape, you could technically represent any algorithm regardless of complexity. But with finite tape, you hit computational limits, right? You can see a physical representation of this mathematical model in the image below. You could take the same conceptual model and represent it as a state machine. right? So we use this conceptual model as a mechanism for thinking about what is computable, as shown in this diagram, of a Turing machine. In this particular case, we're just looking at bit inversion, so converting ones to zeros, right? But we're really able to start now thinking about what is computable, what can we actually represent given a finite set of spaces. At first, we use logic a lot to explore the different ways of representing game logics, what we now think of as game theory. Game theory, after all, is just the modeling of interactions among agents. In the 1959 paper, Some Studies in Machine Learning Using the Game of Checkers, we actually found the first definition, the first documented use of the term machine learning in Western computer science. So in this image, you can see how the author A.L. Samuel codified a tree search-based approach to arriving at the correct move in a game of checkers. One move leads to another, and it sort of starts to change your possibility of getting either a larger or a smaller score as you read through the graph. In this paper, he actually went on to describe how you would actually codify this logic using an IBM computer, right? And you would use symbolic language, right? This was super incredible. This was a completely novel way of thinking about this, right? We were taking these mathematical constructs and then using these human readable terms to actually represent that same information. He demonstrated a way in which machines could learn, albeit very naively in retrospect, but it still discovered the right answer, so to speak. It was search at its core, but it was learning in its behavior. So this approach can translate even now to all sorts of other games, right? So we see tic-tac-toe represented, again, using the sort of tree-like structure as an exercise in search. Yeah. These approaches set the scene for a lot of symbolic AI, as well as machine learning. And these found applications in game theory, search, and even pathfinding. In the late 60s, while building the Shaky robot, researchers needed to create algorithms to help the robot actually plan its own path, and out came what you see in this image, the A-star search algorithm, right? It uses graph traversal to find the shortest path from point A to B, and students still implement it today as part of their foundational education in computer science, right? So we use this family of approaches for all sorts of modern applications. We have, in this particular example, a pseudo state space graph showing us what a vacuum robot world might look like, right? So we have it's a two-cell world, we have a vacuum cleaner agent, and it's sort of showing us all of the different ways in which it might go about cleaning up this world. Similarly, we have another example in which we're really just thinking about route finding, right? So thinking about the simplest, shortest path from point A to B. But a big part of creating systems that can reason, that can think, is not just about finding optimal paths from point A to B. It also involves rationalizing how we represent information and also providing rules for reasoning, or heuristic. The 1959 General Problem Solver program was one that was designed to solve logic programs using a method called means end analysis, in which you basically describe the correct steps to solve a problem. And in this particular case, the goal was to be able to solve mathematical problems like trigonometry and calculus and the like. So let's walk through this example to see how we can create an expert system that is a suite of algorithms, variables, and rules. So the first thing that you need is a vocabulary for actually describing the task environment. Think about these as your nouns that let you actually represent your problem space. Next in your vocabulary, we need to describe processes. Think of these as the verbs that describe method and evaluation and so on. In this flowchart, you can actually see how you might organize executive functions, so to speak, of the general problem solver. From there, you need to describe the relationships between these and the code itself. So how do variables change? How does the math work? What is the connective logic? Your goals then describe how you actually want to move from an initial state to a goal state. I mean, we've seen this before, right? We've seen this in the context of loops and control systems, and we even saw this just now in the state machine diagrams from earlier. On the top is a human-readable description of the goal, find a way to transform object A into B, and then below, you see the logic for what would then become the machine-readable code to chain these goals together. So the final piece of the puzzle are the heuristics. These are the rules that govern For instance, the order in which solutions are examined to decide how or what needs to be ruled out, or what are basically unlikely possible solutions. The authors describe heuristics as things that aid discovery. But it's important to note that heuristics are just guides, right? They provide this sort of practical knowledge, A plus B equals C, but they don't really work outside of that well-defined problem space. Imagine trying to represent the rationale for how you even decide what to wear each morning using a set of rules. There's always edge cases and fuzzy logic involved, and sometimes you just want to wear something. This makes the task of discovery and understanding systems of heuristics especially hard, including when you're doing the heuristics of an expert, say a doctor. So we need to really be able to think about how to define a range of heuristics necessary to solve a problem, learning when to be specific versus general, figuring out which rules people actually use and follow. In a lot of ways, it's almost like teaching a class, right? You have to decide how much is too much and what is just enough to allow for, in our particular case right now, a machine to be able to do the thing that you're teaching it to do. So a lot of what we've talked about so far has been an attempt at really conceptualizing the notion of symbolic AI, right? That is this idea of machine representation of human concepts for us to then be able to implement rational decision-making and reasoning. And there are a couple of pieces that we really need in order for this to be possible. The first is the machine needs to actually be able to understand humans, that is, parse, process, and use language, images, and other forms of human input. Next, we need to be able to actually teach the machine how to represent knowledge, right? So structure, store, and then access those concepts as needed. Finally, the machine actually needs to be able to ask questions and make rational decisions. This is known as automated reasoning. When we integrate all of these different steps, that's really when we are able to actually create what are known as intelligent agents, right? Machines that are able to interact seamlessly with humans, ideally, potentially even passing something like the Turing test. But let's kind of go back down to the fundamental building blocks of all AI systems, and that's data. Data are defined as symbols that represent the properties of objects and events. And so if we take, for instance, this specific piece of land, in my example, this is actually a farm, you can think about data as being representing different parts of this system, right? It could be a specific point in space and time. It could be a system as a whole during that particular point in time. It could be a subcomponent of the system or the system's behavior over a period of time. Really, different types of data have different kinds of spatiotemporal scopes in the world around us. I love this definition that actually comes from the Army Research Lab because they really talk about this idea then of the varying forms that data can take, right? So data are, in effect, any recorded information, regardless of the form or method of the recording. That means that we're actually including everything from images and text to even audio recordings, even observations that we make about the world around us. So let's now start to stack a couple of these pieces. If we all agree that data are observations, information can be defined as processed data, right? That's data that we've formatted, structured, organized, and contextualized in some fashion. Knowledge is then a mix of these things, right? It's a mix of information, of understanding, capability, experiences, and even skills and values. And you can really think about these two different kinds of knowledge that we're usually trying to codify. There's explicit knowledge, this is sort of like knowing what a thing is, and tacit knowledge, which is really critical for reasoning, right? Knowing how a thing actually functions, for instance. And if we really want to be able to go all the way to being able to actually represent data through to wisdom in a way that a human does, we can really then start to define wisdom as this expert knowledge and judgment about important and difficult things in the world. If we layer in the different kinds of technologies that we create, I think of data collection tools as those that allow for us to really collect those observations. Management information systems allow for us to really manage that processed data. Tools like decision support tools, recommender systems, and some of the more rudimentary machine learning systems are really trying to help us sort of pick apart different kinds of knowledge and interrogate our existing knowledge. And really, when we're thinking about moving from expert systems through to building more true artificial intelligences, we're really trying to actually codify, this more esoteric concept of human wisdom. And it's not to say that everything has to be in this particular order, but I find this to be a helpful framework for thinking about where and when we're building different kinds of tools and how they relate to the different kinds of data, information, knowledge, and wisdom we have about the world around us. So a core component of what we need to be able to do in order to build AI is to be able to represent knowledge. Consider this high-level architecture of an expert system. In this particular case, you can see that we're sort of taking input from a variety of experts, representing it in some sort of knowledge base, using some sort of inference engine, right, some sort of reasoning mechanism to then provide a user with the ability to be able to ask, in effect, the expert's questions, but it's really right mediated by a piece of technology. And so we'll kind of look at a couple of these different components specifically so we can kind of understand how they stack together. So let's focus first on knowledge itself and how we represent it. So let's look at a couple of examples of how we can represent knowledge. In this particular case, let's actually start at the bottom. You see a little circle that says the word Jessie in it. This is Jessie the dog, right? Jessie is a golden retriever. We're moving up the graph. A golden retriever is a type of dog. A dog is a type of mammal. A mammal is a type of life form. This very simple example allows for us to start to represent what we know about Jessie the dog in the context of the world around us. This is one way of representing knowledge. Let's look at another. In this particular model, we actually have 5 objects, even though there are 2 humans in the mix. There are 2 binary relationships between some of these objects, right? There's a brother, and then there's something on somebody's head. There are 3 unary relationships. So there's a person, there's a king, there's a crown, and then there's one unary function, that is the left leg. In this particular case, we're both representing the objects, we're representing the relationships among them, and then we're really able to then start to interrogate this specific model to be able to ask questions like, who is the king, and who is whose brother, and so on and so forth. This form of representation, right, this idea of representing concepts and the relationships among them is known as an ontology. So ontologies have been used to represent a wide variety of very real concepts and the relationships among them. This specific example is actually from the crop ontology, which is an ontology that allows us to represent information about a variety of crops. And a lot of the data that you're seeing here is scientific data. So we're looking at an example of the apple trait ontology that was curated by a group of researchers. And if we look on the bottom, you can kind of see some of the variables, right? Some of the attributes that we have about the apple. So we can think about agronomic variables, the date of harvest, the fruit starch average, and so on and so forth. We can even think about quality attributes, right? These are very structured concepts about the apple itself. And so it means that if I now wanted to be able to represent a banana trait ontology, I might actually want to start to follow this similar structure, right? So in a lot of ways, ontologies are an attempt at allowing us to create structure to represent knowledge about the world around us. And this is really important because we also want to be able to start to disambiguate among concepts. If I tell a machine that this is data about an apple, it needs to be able to disambiguate between, is this a poison apple? Is this apple the computer? Is this apple the school in Minnesota? And so on and so forth. So this example actually shows you a snippet from DBpedia, which is an open source knowledge graph project, which actually tries to represent information that we have collected on Wikipedia in a structured format, right? This means that we're now able to start to actually teach a machine how to disambiguate among concepts like you and I might naturally or intuitively do. This then allows us to actually start to link different kinds of data to be able to create meaning, right? If I know that we're talking about apples and cheese, it means that I can actually create a model that allows for me to build a pizza in this particular case, right? Each of those objects have specific things that they can and cannot do, ways in which they can be combined, ways in which they relate to each other. It means that if I want to build you a spicy pizza, I know which types of ingredients I should be avoiding and which types of ingredients I should be encouraging, right? And so we're now able to start to use this ontological representation of these fundamental properties, right? These fundamental objects in the world around us to be able to then create more meaningful things, in this case, pizza. So there's a lot of functional utility of ontologies, right? You can use it to be able to build systems to help you interrogate data, but you can also use them to build systems to help you, right, do science at a much larger scale. This particular example is actually a subset of the gene ontology. I truly love the gene ontology. I think they do a fantastic job at demonstrating the power of structured representation of data, right? There are so many complexities in genetics. So in this particular case, and we're just looking at a subset of their biological process ontology, we're able to start to think about how different types of scientific experiments, different types of understanding can start to be connected, right? And so it means that we're able to reason at a much higher scale than just at, what happens in this very specific small part of the universe. And so as we start to represent knowledge around us, we're able to kind of zoom out and create these models that represent more than just the tiny slice of the universe that we might know of. So we're really setting ourselves up to be able to build tools that can engage in some level of automated reasoning, right? If they know the relationships between the concepts in our knowledge base, then we can start to really focus on inference, right? Thinking about what does that mean, or how can we do that next step? So I'll just give you a really quick example, mostly from NASA's work that looks at automated reasoning. This particular graphic kind of shows you the breadth of ways in which we can think about reasoning, right? In this particular case, again, we're looking at, the application of reasoning to integrated vehicle management systems, but I think lots of the lessons can apply to other spaces, right? So consider how this might look in your specific domain. So if you look at sort of this core idea of reasoning, a lot of the fields that we might need to be able to think about may include things like troubleshooting or incident reporting, diagnosis, job scheduling. If we go to the red circle outside that, there are then applications that we actually might want to build out, right? Whether it's an application to be able to think about drivers' behavior or, a game like StarCraft, and so on and so forth. And then if we zoom out to the outermost layer, you can kind of start to see the different industries that might use those same reasoning concepts. And so it means that even though the examples that we're going to be looking at in this particular case are coming from, right, vehicle diagnostics, I'm hoping that you can kind of see that ripple effect of how each of these different forms of reasoning can apply to other disciplines and problem areas. So we'll actually start with rule-based expert systems. Earlier on, we talked about different ways in which you can represent information about the world around us. Part of the reason why that's incredibly powerful is because once you can start to represent information in a structured fashion, you can then start to be able to actually reason about it. So in this particular case, I think it's a pretty funny example. This is a proof that curiosity killed a cat. And so you can see that there's a couple of different relationships that talk about who loves whom, whether it's, Jack and the cat's relationship with Tuna, and so on and so forth. But it means you'll really be able to then kind of pick apart what the ripple effects are of one thing with another, right? Right. So the first applications of this sort of formal logic were as rule-based expert systems, where you can really think about an expert system as code that is designed to mimic the decision-making of a human expert, right? So while early expert systems integrated game theory and search, like we saw before, they used pathfinding logic to be able to navigate to like the right choice in decision trees. Lots of different things happened after that, right? So let's look at this very simple example, right? It shows us how a tree-based logic can be applied to a simple decision-making problem, in this particular case, right, to determine payment for chores. Conversely, this is ELIZA. This is actually the first chatbot that was released in 1964. And it was essentially a heuristics-driven expert system that integrated pattern matching, natural language processing, and lots of other things to provide a simulated conversation. And so pictured, we actually have the doctor program, in which she was given like a set of heuristics that describe how an expert psychotherapist of the Rogerian school might actually conduct therapy. So using reflexive questions where the patients basically ask, why? Why do you feel that way? Tell me more, right? So lots of reflective questions to be able to guide a line of inquiry. And so this prototype was interesting because it demonstrated right, how heuristics could be used to actually guide a basic expert system, and then B, the combinatorial explosion challenges that would ensue as you start to begin to think about how to integrate more and more heuristics, right? And the final thing that it also showed us is the potential problems that might happen when you start to create tools that could fool a person into thinking that they were actually interacting with a real doctor. But there were many, many other use cases that did make sense. And so we'll look at some of these other use cases in a bit more detail in a moment. In this particular table, you can see a quick summarization of the different categories of expert systems. Granted, this was a table summarizing a book written in 1983, but I think the categories are still, right, very reflective of the types of things that we're still designing AI systems to do, right? So this should, again, remind you of that circular graphic from earlier where we're looking at the different application areas and the different industries that have been influenced and affected by a lot of this formative work that was done in expert systems. So let's kind of dig into some of the more concrete examples of the expert systems that have worked really well. Consider first the design of a spacecraft, like the NASA Voyager that is pictured here, right? It's a very complex system with lots of moving parts, a lot of scientific and engineering effort went into it. It is a very high value item, right? So it's a complex systems engineering project that really required us to be both methodical in the design, in the modeling of it, and even in the evaluation and testing of it before we kind of just, release it into space. And so to be able to manage the complexity of the system, NASA engineers developed the spacecraft health inference engine, right? There were probably many other things that were developed, but this is one of them we'll focus on. SHINE was basically an expert system, right? It was an AI program designed to monitor the health of space systems. In this particular case, it compiled knowledge into a compact representation. It was natively executed on the user's computer, and then it was used to be able to interrogate, right, to be able to find bugs in the model itself, whether it was, what happens if this particular issue arises, or what are the ripple effects of this particular thing disappearing, and so on and so forth, right? It allowed for us to interrogate the model of the Voyager system under different scenarios. So this was, in effect, an expert diagnostic tool. And it was kind of amazing, right? When Voyager was actually in approach to Neptune, the SHINE system actually discovered an anomaly, and it allowed for people to then be able to actually fix the issue in advance. And so it's a really powerful example of how, even at a distance, if you have a really good system that allows for you to interrogate your models, you're then able to really do even diagnostics, right, at a distance of, between here to Neptune. And so since then, NASA has really used a lot of these kinds of tools to be able to monitor lots of systems, and there's a lot of other applications of this core work, right? But an expert system is in effect codifying the expertise of a large number of people. I'll read the quote from this article about it, right? They said, it's as if rather than calling in an entire 100-member advisory team to solve a given problem, one sends for just 2 of the specialists needed to address a specific issue at hand. Right? And being able to actually build an expert system that allows you to do that without necessarily obsoleting your entire process is a really, really tough thing to do. And so for me, at least, the SHINE system demonstrates how you can use technology as a mechanism for being able to actually capture the knowledge that is in your group, allow for you to do some of these more time-consuming things without necessarily stressing out your entire team, right? So thinking about expert systems as supportive of the enterprise that you are engaging in, as opposed to a replacement for your entire team. And for me, that's one of the takeaways that I'm hoping you'll kind of keep as you're looking and thinking on what does it mean to actually develop expert systems that codify the knowledge of different types of folks. As part of NASA's interest in tech transfer, this technology actually ended up getting patented, and then a company spun off from it. And so they actually took this core concept, right, a tool designed to be able to diagnose issues in a system, and they applied it to targeted advertising, for better or worse. And so in this particular case, somebody saw the technology, and they actually then repurposed the core inference engine to be able to then answer a couple of different other questions. So their first application was targeted ads, and then they actually ended up building out an entire company that looked at the industrial decision support. Right? And you can kind of see how some of the same types of paradigms might transfer, right? In the space system, in the space example, we're looking at diagnostics of a specific vehicle. In this particular case, we're looking at diagnostics of actually the process flow within a refinery, right? So thinking about optimization of the refinery processing workflow. And so a lot of the fundamental building blocks of many of these systems translate across disciplines. And so you'll see families of algorithms being used in very, very different use cases. Another thing that I thought was really significant about some of this early work that NASA did and others did in expert systems is you can kind of see the impact it had on many different areas of AI research and development, right? These early expert systems kind of paved the way for us to be able to dig into machine learning, a lot of that early representational work paved the way for us to think about the knowledge representation at scale. And these pieces combined really started to sort of pave the way for different kinds of AI explorations, including modern self-driving cars and natural language processing and so on and so forth. But one of the biggest challenges with expert systems, right, the core challenge with rule-based expert systems is a concept known as computational complexity. And that really helps us think about what the challenges are with the representational capacity of machines. So in this particular quote at the top, the phrase Turing complete is used to describe systems that can represent anything, so to speak, right? And mathematical problems are considered computable if they can be solved in principle by a computing device. But a combinatorial explosion happens in complexity when you start to actually try to represent everything, everywhere, all at once, right? And so if you look at the questions that we have in here, right, there's two examples. One of them asks you to think about, if you have a particular formula, what does a satisfying assignment mean, right? Does it mean everything possible, or is there a limit to the number of answers that you would consider acceptable, right? Let's think about the chessboard in the next example, right? If you have a chessboard of size 2 by 2, that is one level of complexity that you have to represent. If you have a chessboard that is 1,000,000 by 1,000,000, now being able to actually calculate a winning strategy becomes this very, very complex process. So you can kind of see the sort of like the explosion, right? That growth problem that I was talking about in this particular graph, right? And this is just a checkerboard. You can see that growth of the checkerboard problem state space, right? The computational complexity increases dramatically as you go from a 2 by 2 checkerboard to something that is significantly larger. It means that we have lots of problems that we describe as being possible, or rather tractable or intractable. And so if you've heard the phrase NP complete, we're really talking about problems that can be solved in polynomial time versus non-polynomial time, right? That's a computational capacity. Can you actually solve this in a meaningful time? And this is an entire body of research. I don't want to go into this too much more, but I really want you to be able to come away from this being able to just think about this idea of computational limits, computational complexity, and have some of these terms sort of bucketed in your brain so that as you start to hear people talk about, for instance, things like NP-complete problems that are really, really hard, you're able to say, yeah, actually, maybe I won't invest dollars in trying to solve some of those problems in the beginning, right? And so really just thinking about what is and isn't possible given the different kinds of capacity that you may have. Right. And so the first so-called AI winter occurred after like a lot of effort went into trying to represent this sort of increasingly large amount of information. Right. When people started to try to represent all knowledge, systems suffered from this combinatorial explosion, a lack of computing power, and processes couldn't keep up. And so this challenge of representing and connecting general knowledge in a structurally consistent manner became increasingly hard. Right. So consider even like the simple example of if you want to explain to someone how you stack your dishwasher in a certain way, you might have to explain lots of different steps. And at some point, if your dishwasher is big enough, you're not going to be able to really explain exactly how you think about it. Right. And so you think about when you're looking at small scale problems, you can probably test to find every single combination to find the solution. But when you start to scale out and you look at these really large scale problems, it becomes practically impossible to find the perfect answer. And so at that point, you really need to start to think about what kind of bumpers do you need to put on your problem solving to be able to then come to a reasonable next step. So the next genre of AI that we'll look at are decision support tools. And you can really think about these as scaled down, scoped well expert systems, right? And so in this particular case, let's look at we're really looking at how humans are using data to ask questions, solve problems, make decisions. And I'll give you a couple of examples from the world of agriculture. So in this particular case, we're looking at a lot of different kinds of data that a farmer would actually use to be able to make decisions about how to adopt crops that help their soil become more healthy and other things, right? So cover crops are these plants that are used to actually manage sustainability in agriculture. Right. And so they're having to actually interrogate a whole bunch of different types of data to be able to actually make a decision. And so one of the things that we did was actually built a decision support tool that kind of takes all those different kinds of data together, allows for a farmer to basically draw up their field. We then pull, right, supporting data from things like soil databases that are hosted by the USDA. We pull in weather data from NASA weather data sets. We invite the farmer to give some specific goals that they have about their field, and then we really subset that list of crops, right? That original set of data down to the things that they might actually need. And so at least in our work, we really think about this idea of, right, how can you engage in decision support to nudge people towards towards more sustainable decisions, right? You don't necessarily want to give them that flood of data. You don't necessarily want to say this is the perfect answer, but what you really want to be able to do is say, here are a selection of answers that you can now go talk to an expert a little bit more productively, right? You're able to actually begin that conversation with your advisor as opposed to necessarily just saying, I don't know, and going completely cold. So we're really thinking about the sort of like spatiotemporal scope of decision making, right? And this, again, even though my example is from agriculture, I think this particular graph especially, and this way of thinking about decision support applies to many other fields, right? So if you think about the spatiotemporal scope of decisions, we're sometimes making these really highly operational decisions that have to happen right here, right now. We're sometimes thinking about these tactical decisions that have to happen in the next couple of days, maybe months, at a slightly higher, higher scale or a slightly larger scale. And sometimes, ideally, we're also thinking in this really long-term strategic fashion, right? Trying to think about what's going to happen, not just next year, but many years from now, not just at the scale of my landscape, but of entire global landscapes, right? And so thinking about decision support as being scoped based on, right, the spatiotemporal resolution is a nice way of saying, okay, my system does not have to represent all data about everywhere all the time, but really, I just have to make sure that my system is supporting that constrained form of decision making. So let's look at a couple of examples now of decision support in the medical field. This is an example of a tool used for patient health management. That's actually, right, it's modern mental health software. And it's really oriented towards mediating provider-patient interactions, right? So somebody would basically have their dashboard, they would have their clients in here, they would then construct these different kinds of forms to be able to allow for a person to actually provide some structured responses. And then they would actually use that information to then determine when and where, how they might want to actually interact with their patients, right? And so you're in effect allowing somebody to create this provider-created rule set to gather patient data to then manage those interactions. And so even though this mostly looks like a web form, underneath the hood, there are a variety of different machine learning algorithms at play that determine priority and what types of things are being shown on the screen and so on and so forth. A slightly more complicated example is shown here in this patient data annotation system that allows for a medical provider to be able to basically take an image of a patient and then label and to provide some basic labeling and annotation. So that way they're able to, for instance, look at somebody's spine and be able to determine when and where different kinds of issues arise. In this particular case, this tool is basically using what's known as fuzzy decision support, right? So it's kind of using some fundamental rules to then be able to say, okay, you might want to look in this particular direction, even though it's not necessarily making any recommendations about what comes next, right? This is really just a data collection tool with some fuzzy decision support on top of it in the form of image labeling and annotation. A slightly more advanced example in the same genre of tools is this particular decision support system that a doctor would actually use to search for disease patterns in different kinds of lung images, right? Lung CT scans. And so it provides different kinds of measurements to add sort of a little bit more detail to a radiologist's report, and then allows for them to really sort of move towards some sort of diagnostic information, right? So in this particular case, we're looking at patient data diagnostics with added computer vision decision support, again, with a family of algorithms working behind the scenes to be able to provide, right, in this particular case, a radiologist with a little bit of guidance about where and how they should be focusing their attention, right? And each of these tools have been, there's different levels of success and adoption in different communities. And so these examples have been shown, not to say that this is necessarily the only way or the right way to engage in decision support, but these are good examples, I hope, that demonstrate how you can scale down, right? Scale down that spatiotemporal scope of decision making and say, okay, I can still build something that is like an expert system that takes into account the heuristics of an expert, but really is designed to support expert decision-making or to be able to support interactions among people and the experts that they might consult for different kinds of decisions. There's a company called Psycorp that is one of the oldest companies when it comes to thinking about symbolic AI. And a lot of their early work was really focused on building ontologies, right? They were hiring philosophers to codify, interactions among concepts. And a lot of their more modern work has now really looked at being able to actually integrate those heuristics approaches into other kinds of workflows. So in this particular example, we're looking at one of the tools that they've built that engages in that engages in machine reasoning using contextualized data, right? And so we're looking at, how would a person actually move through a hospital depending on what they needed. And so the tool is, at least from this demonstration, showing us how it might do things like suggest priorities, suggest order of operations, suggest when somebody needs to be attended to and by which expert. And so you're really looking at this sort of like machine reasoning tool to allow for the management of fairly complex workflow. And I would say the workflow management is one of these larger areas, right? Whether it was in the example of industrial decision support with a refinery that we looked at right at the beginning, or even this one, right? But the sort of like workflow management, process management is an area where I think decision support tools have really shone because they're able to actually allow for somebody to engage in, right, optimization of an expert process that has already been partially codified because we have, right, processes and protocols for like everything. But one of the things that I also really like about their group is this idea of, being able to actually integrate logic and patterns, right? It's not, there were a lot of challenges with earlier work on machine reasoning that relied on representation of information, specifically around sort of like combinatorial explosion. And so even though a lot of the early work on symbolic AI was really criticized for being overly structured and relying on a lot of representational capacity, there are still a lot of lessons that we can learn for it, right? Using those sorts of heuristics can allow for us to guide the different kinds of machine learning systems that we will build. And we'll explore these a little bit more in some of the subsequent sections of this course. So creating machines in the image of humans is rife with challenges, including how to represent our rationality. Humans make decisions by satisficing, right? So that figuring out when an answer is good enough to act. Machines, and quite frankly, humans too, can get trapped in this idea of finding the perfect answer. And so Stuart Russell, an AI researcher, offers the concept of bounded optimality as a concept for defining intelligence in machines, right? But with this idea of accepting that a machine is finite, so too comes a challenge where we have to make sure that we are communicating with each other and the machine what those constraints are, how they exist, why they exist, and how that affects our ability to actually use and interact with machines as decision support tools, right? Knowing what the bounds of a technology are, and at what point should we stop relying on the tool and start relying on each other again. So symbolic AI has actually come a long way since then, and we're now seeing this transition to many more hybrid approaches. And we'll look at some of the details of these cognitive architectures when we talk about neural networks later on. But I at least want to show you some of the ways in which people started to take the lessons from symbolic AI and integrated them into some of the more neuroscience-informed architectures for computing, right? And so in this particular case, we're looking at a fairly famous cognitive architecture known as the SOAR architecture that was directly inspired by that general problem solver program that we saw earlier in this lecture, right? So John Laird and his team have been working to try to think about how we can then start to actually bucket some of these different components and start to treat it as a modular system. right? So in this particular example, their paper looks at some of the different emerging models of cognition, thinking about how we can separate concepts into different kinds of memory and perception and action, and then start to actually link these components together to still allow for us to do things, for example, right, represent some heuristics that govern relationships in a finite space that still allow for us to be able to represent things using heuristics that govern a finite set of concepts, but still allow for emergence to occur, right? For things to arise from the data itself. And we'll spend a lot more of this course really focusing on the latter, especially since the sort of evolution of symbolic AI really sort of paved the way for us to be able to then start to integrate, right, expert systems with emergent systems. For the next few examples, I'm going to refer to a book by Russell and Norvig called Artificial Intelligence, A Modern Approach. I find that the examples are a very productive way of introducing each of these concepts. In their book, they define an agent as anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. The robotics agent, like we've heard about before, may have actual sensors like cameras, but a software agent, like a chatbot, may only have text input, for instance, that a human provides to it. So there are a range of actions that are available to an agent based on the full set of observations of the environment that it has to date, as well as perhaps whatever knowledge we may have previously provided to the agent, and perhaps even heuristics or examples via training data. So we can really consider the task environment within which an agent is performing. Here we have a couple of examples that allow us to kind of think through this problem. So we have an agent type, then we have a performance measure, that is, how will it determine what the right or rational thing to do is. Then we specify an actual environmental condition that the agent is constrained by. Then we have actuators and sensors that describe how the agent will act and how the agent will receive and perceive input. So if we take, for example, the part-picking robot in row 3 of this table, we see that the performance measure that we're going to use is the percentage of parts in correct bins. The environment is the conveyor belt onto which it is, bolted onto. Its actuators are the arms that it used to pick stuff, and the sensors are cameras. But if we take the bottom most example, the interactive English tutor, this is more like a chatbot, we can still use that same structure, right? So the performance measure in this particular case is how well a student scores on their test. The environment is actually the students that it's teaching, as well as the testing agency, so whatever the rules of the tests are. The actuators in this particular case are the exercises that it will display, the kind of feedback it gives, the kind of speech, and the sensors are, right, that keyboard entry and perhaps even voice input from the students themselves. When you think about the task environment, there are then lots of different factors that you can actually consider to determine how hard of a problem this is actually going to be. Certain environments are fully or partially observable, so you can think of, even let's take the example of a modern search engine. It only has access to whatever information on the internet it is allowed access to. Right? But if you're doing search within a very constrained environment, then that knowledge that it does not have access to is not within its observable space. You can think about single versus multi-agents. So is this a single bot acting, or do you have multiple bots competing, right? So think of like a video game where sometimes the bots are helping you do a thing, whereas other times you're fighting them to make it to the princess. We can also think about task environments as either being deterministic or non-deterministic, which boils down roughly to can you predict the next action based on what has happened so far? We can also think about episodic task environments versus sequential. So are there dependencies amongst the actions? Can we chunk them into episodes, right? Is it modular? Some environments are also then static versus dynamic. So is the environment changing during operation? A classic example of a very dynamic task environment would be one that an autonomous vehicle has to be in, right? There's people, there's trees, there's clouds, there's snow. It's like a whole thing going on. The next factor we can think about is discrete versus continuous, right? Are these time steps or an ongoing progression? Are these time steps or an ongoing progression? So when you're running a simulation, let's say you're trying to simulate the way in which a crop grows, You could either, start the simulation and say time is moving continuously, or you could say, I'm actually just going to increase the time by a day at a time, right? So in steps. And the last thing that you can really think about is this idea of what we know versus what we don't know. There's a quote that I'm losing my reference for right now, but it's this idea that, uncertainty is the only form of certainty that we actually have. This makes the task of figuring out how to code an agent system fairly complex. And if we put all of these different cases together, we can say that the hardest case really is one where the task environment is partially observable, you have multiple agents, it's non-deterministic, it's sequential, it's dynamic, it's continuous, and it is very, very much unknown. And so one of the things that we want to do as designers is try to think about how we can then start to reduce some of the complexity in our task environment. Let's now look at a sequence of agent types where we increase the level of complexity or autonomy of the agents themselves. So the first one that we're going to look at is a simple reflex agent. This is an agent that responds directly to what it perceives, right? See obstacle, move. Receive search requests for items, provide search results. They're following simplistic if this, then that logic. A very basic example of a simple reflex agent in action would be the whack-a-mole game, right? You see the thing, you knock the thing down, and it pops back up again. Nothing very complex is happening here. But given that machines or agents cannot track or observe everything, we need mechanisms to help them keep track of what is known and perhaps even what is unknown. So a model-based agent uses its internal state to then make decisions, making estimations about what might be possible. So let's think about a video game where you are shown parts of the world that you've already discovered or explored, or a vacuum robot that discovers, so to speak, the shape of your living room. An example of a model-based reflex agent in action would be even just the game Pac-Man, right? But in this particular case, the model-based reflex agent is not us playing Pac-Man, it's the ghost in this particular case, right? They're reacting to the state, they're finding me, they're chasing me, they're really looking at the model of the maze, the current state of the maze, as well as using a set of predefined patterns to be able to then determine where and how to foil me. Then we have goal-based agents, right? So goal-based agents are using an additional programmer, user, or self-defined direction to really determine what happens next in addition to that internal model. So in this case, the actions are determined by whether or not they fit a higher level goal, not just by an immediate reaction. For instance, a goal-based agent will brake when the red brake lights in the car in front of it are lit because the goal is to not hit other cars, not just because there exists a red brake light, right? So a goal-oriented agent really provides directions that include, for instance, a scenic route if the user requests that goal be met, right? So you can really define goals and then use that to kind of guide the recommendations that come out. An example of a game in which goal-based agents are in action would be The Sims, right? So here, a player is controlling virtual characters and we're creating our entire world, but the game's goal-based agent operates each sim, allowing them to decide to pursue different kinds of goals, advancing their careers, forming relationships, right? There's this entire universe around you with these other goal-based agents, including you and your own characters. Next come utility-based agents. These are more complex, and they try to maximize their own, or depending on how you define it, a user's expected happiness. They're mostly experimental, quite frankly, at this point in time, but a machine really needs to be able to negotiate perception, reasoning, representation, and learning. And as we know from, philosophical explorations of the human quest for happiness, even if you can define utilitarian or Kantian functions for how to maximize happiness, sacrifices are made because it's a much more complex problem than simply saying, do X because it will improve Y units of happiness for Z agents. Still, there are games that do try to implement this utilitarian approach. And so an example of this would be the Civilization series, right? This is a real-time strategy game in which you're creating your civilization, you're making decisions to maximize that overall utility for yourself, but then all of the game characters are doing similar things, right? So resource management, technological advancement, all of these different strategies are based on the utility of different outcomes, right? So while you are being utilitarian and potentially in your approach to playing this game, the computer, right, those non-player characters are also taking a slightly more utilitarian approach to interacting with you, where they're trying to really maximize their ability to just dominate the universe or the world. Okay. So in our quest to develop AI, each of the types of agents we've discovered so far can be implemented also as a learning agent, where performance measures are integrated to really guide a machine to finding the right answer. So the design of these performance elements really ends up involving a balance of factors, right? So human, social, global factors. We really have to think about what it means to teach a machine to act rationally and then to have an internal model of what is right? Much of this course will be spent really thinking about how we should be defining different kinds of performance elements and learning elements and deciding how to really bound the search space or bound the state spaces for different kinds of agents. But let's look at a fun example that actually takes some of these ideas and puts them in action. So this is the game StarCraft 2. It's a real-time strategy game where a player basically controls a bunch of spacey units, and you're engaging in different kinds of battles to be able to achieve, again, total victory and domination of the universe. So the game actually has a very sophisticated AI, and there are lots of different opponents that are acting as learning agents. So they're adapting their strategies and their tactics based on both historical gameplay data as well as encounters with other players, as well as their interactions with you. And so there's a whole suite of different kinds of machine learning algorithms underneath the hood that allow for your opponents to become increasingly challenging over time, sort of like the SAT sometimes. But in this particular case, we're really just providing players with this dynamic and engaging gameplay experience. I'm not sure if anyone has noticed so far, but I actually have small descriptions of each of these games as learning agents below. And I actually used ChatGPT to generate these examples. And I thought it was really interesting to have these conversations about how each of these games are or are not functioning as different kinds of agents. But we'll save that conversation for another day. I just wanted to point out that funny little thing that's happening at the bottom. But let's take this general learning agent and see it in action a little bit more. So in 2019, Google released an AI known as AlphaStar. And the goal of this agent was to be able to play StarCraft 2 against the top esports player at the time, Mana, in a game of StarCraft 2. And so you can see a few of the stats of this fellow. He was quite accomplished. Esports is a thriving area. If you haven't been watching, there's an entire industry around electronic sports. And so in this particular case, Google decided, in the spirit of pitting AI tools against humans and playing chess, as we've done in the past, or other games, they decided to try something a lot more complex. And so they actually had their tool play against this guy at StarCraft. And we can kind of see a little bit of how it went. I guess the spoiler alert is the AI won. In fact, many modern AI systems have actually been beating humans at these sorts of games, which is very interesting, right? Because these are real-time strategy games, right? As we've discussed so far, they involve utilitarian methods, there's goals, there's an internal model that has to be built. And this sort of decision-making, their strategies are really emergent properties. And we'll talk much more deeply about how neural networks work and why this sort of genre of artificial intelligence is very interesting. But you can kind of see the complexity of the decision-making that is in action, both on the part of the human and the machine. Here's a really nice graph from the Google DeepMind blog, where they actually give us a download of exactly how this worked. Well, enough of how it worked for it to be interesting for us. And you can see some things that we've seen before, right? So at the bottom, you have this tech tree, which actually shows us, what the different options were if it implemented a gateway or a cybernetics core, right? Each of those are actually game components, right? So it was making a decision about whether or not to do one thing versus another. And so you can actually see the strategy map as the AI was actually deciding what to do in order to win the game. We can think of this as a modern day version of that chess map from right at the beginning, where we have used AI tools to try and think about what the optimal method of winning a game is. But this is cool, right? These are very complex games. And now we're asking our agents to start to reason, to start to rationalize, to start to strategize.